Hello everyone, welcome to the introduction for the analysis of variance, otherwise known as ANOVA. We will more specifically be focusing on a one-way ANOVA. There's more than one type of ANOVA, but for our class purposes, we just conduct one-way ANOVAs, and that's what I'm going to focus on. So the video will give you the background about an ANOVA and then how to conduct an example one in RStudio and a little bit about the interpretation of said ANOVA. Again, remember that statistics is actually a critical component of the scientific method, right? We use it to describe our data, right? So we summarize scientific information with descriptive statistics. We use it to estimate parameters of populations because we can only subsample those populations. We can't sample everyone in the population, right? And then we also use it to test our hypotheses. This is inferential statistics, right? We have a research question that we got from an observation of nature. We develop a testable hypothesis. We design an appropriate experiment and collect data. And now we have to test that hypothesis, right? We use inferential statistics to do that. Again, remember that if this blue shape here represents all of the individuals of a particular population, right? So this is capital N, all the possible data points or individuals is the population. Most of the time we are sampling that population, right? We're pulling out subsets to quantify because it's logistically impossible to sample the entire population, right? Our goal is to design a thorough experiment with a large enough sample size to get a good representation of that population, right? And so we're estimating parameters, which the parameter is the true value in the population. We're doing that through statistics. That is our estimate of the population attribute. Also remember that we need to keep in mind that there's a chance we're wrong, right? So there's type 1 and type 2 errors. Type 1 error is alpha error, or the false positive. This is the error of rejecting the null hypothesis when it's actually true. So we're going to say that there's maybe a difference between groups or that things are not equal when in actuality they are the same, right? So again, a false positive. We define this cutoff by giving you a specific alpha value, right? And the most common alpha value is 0.05, right? So when we say the p-value is less than 0.05, then we can reject the null and accept the alternative hypothesis, right? That's sort of what's built into us all throughout our student career. But remember that 0.05 is really arbitrary, right? R.A. Fisher picked it. It just means that there's a 5% chance that we're making a false positive, right? There's a chance that we're wrong. In this case, it's a 5% chance, right? There's no reason that you couldn't pick 0.1 and say, well, I'm okay with a 10% chance of being wrong, right? Or making a type 1 error. The second kind, type 2 error, is the beta error. This is a false negative. This is failing to reject the null hypothesis when the alternative is the true state. So we fail to say there's a difference when one actually exists, right? And then again, more importantly, another important aspect to consider is the difference between experimental or scientific hypotheses and statistical hypotheses, right? Throughout the semester, we have you work on writing better experimental or scientific hypotheses, right? It's a biological relationship between two or more variables that is testable or falsifiable, right? We practice writing those. Those are different from statistical hypotheses. These are statements about whether or not a pattern or a trend or a difference is present in your data, right? So we use a null and an alternative hypothesis when we do inferential statistics. Every statistical analysis that we cover has a set null and a set alternative. This is where we're using that alpha value to cut off if we reject the null and accept the alternative, right? These are not the same as scientific hypotheses. When we ask you to write the null and the alternative, it's not to write your experimental hypothesis, right? These are not alternative explanations for your research question. They're simply statements about what the statistical analysis is testing for. If there's a difference in the means, if one or more groups is different, right? And the wording to these null and alternative hypotheses is specific to what statistical analysis you're doing. The null hypothesis in a chi-square is different from a t-test, is different from an ANOVA, is different from a regression, right? It's important to learn the difference between statistical hypotheses and experimental or scientific hypotheses, and that the null and alternative hypotheses are specific to the analysis that we're doing, and it helps frame our inferences of the results of that analysis, right? The null hypothesis, also referred to as H naught or H sub 0, typically states there's no pattern, there's no relationship, there's no dependence, right? That basically group A and group B, or these two variables are not related, right? So that's the null hypothesis. Again, the wording changes depending on the analysis that we're doing. The alternative hypothesis, often denoted by HA, right? Usually states that there is a pattern, there is a difference, there's a dependence, there's a relationship. Again, depending on what the analysis is, the wording is different. And again, it's important to take the time to realize these differences and really think about, do you understand the difference between a statistical hypothesis and an experimental hypothesis, and when it's appropriate to bring up each one, right? When we talk about interpreting the results of a statistical analysis, you really shouldn't be jumping right to your experimental hypothesis. Our accept and reject statement should reference the null and alternative hypothesis. Okay. Again, we're back to our statistics roadmap. Hopefully you've watched multiple tutorials now and you know that I love this thing, right? This helps us decide what analysis is appropriate by thinking about what type of independent variables we have, those are our x's, right, versus our dependent variables, our y. So one categorical, more than one categorical, one continuous, more than one continuous, or a mix of both. Again, the same thing with our dependent variables, and we just find where our rows and columns intersect, and that's the analysis or analyses that are most appropriate given our data. Okay. The ANOVA, or analysis of variance, and again more specifically the one-way analysis of variance is what we're going to be focusing on. This is used to evaluate the null hypothesis that all groups or treatments or populations are equal versus the alternative that they are not, or at least one is different. Okay? The key here is that the number of groups or treatments or populations need to be 3 or more. Okay? If you only have 2 levels of your categorical variable, you're going to be doing a t-test. If you have 3 or more, you're going to be doing an ANOVA. This is used to compare means and variances from several groups, populations, or treatments and test the statistical hypothesis that there's no difference in their means and variance components. Okay? So again, if we go back to our roadmap, we have one grouping variable, which is our independent variable. This could be populations, this could be treatment, this could be species, this could be some other group, right? But it's categorical. It's nominal data against a dependent that is continuous, right? And you notice that t-test and ANOVA are in the same cell here. We do a t-test if we have 2 levels of the group. We do an ANOVA if we have 3 or more levels in the group. Okay? So again, it's important to realize when you do a t-test versus ANOVA, and that's on the number of levels in our categorical variable. Okay? The term one way is referring to the fact that there is only one variable defining the groups. We can do two-way ANOVAs, blocked ANOVAs. There's different ways to do an ANOVA with different numbers and types of variables. We don't get into that in this class. We're simply focusing on one-way ANOVAs. Hopefully, as you move on in your academic career, you will be introduced to more of those. Again, ANOVA takes into account the mean, but more importantly, the variance in the data set, right? So the total variation in your data set is comprised of 2 components. The variation among groups, so the difference, sort of the variance between group A, group B, and group C, and then the variance within a group. So all of the variation within individuals in group A, within individuals of group B, right? That's also referred to as a noise or error variance, right? Because not every individual in a grouping is going to be identical. There's some variance within a group, but we're also looking at variance among or between groups. Okay? The basic idea of an ANOVA is that if the variance caused by the interactions among the groups is larger than when compared to the variation that appears within each group, then it's because the means aren't the same. Right? The null hypothesis of an ANOVA is that all of the means or the groups are the same. So the mean for group 1 equals 2 equals 3 equals however many groups you have. The alternative, and this is important, states that not all of the means are the same. Okay? It doesn't mean that they're all different. It means that at least one is different from the others, right? That means that there's an effect of our treatment or our population or our grouping variable. But it doesn't mean that every single group is different from each other. If we reject the null and accept the alternative, it means that at least one of the groups is different from the other, and we're going to talk about multiple comparisons here in a second and to figure out which group is different from which group. Okay? So again, there's lots of scenarios, right? Is that if the null is rejected, so the null states that all groups are the same, right? Factoring in their means and variance. If we reject that, the alternative hypothesis, depending on the number of groups you have, could mean anything. So in this scenario here, group 3 is different than 1 and 2, but 1 and 2 are the same. In this scenario, 1, 2, and 3 are all different from each other, right? And that's an important detail that we're going to want to know when interpreting the results. And again, in a little bit, we'll talk about multiple comparisons as we go through an ANOVA. The ANOVA calculates an F-test statistic or an F statistic. This is like a t-test, but we've got an F distribution, right? So it's got its own theoretical distribution. We can calculate the test statistic, the F value of our ANOVA, and compare that in the theoretical distribution given our degrees of freedom, and obtain a p-value from that, right? So the F value is found by dividing the between group variance by the within group variance. An F statistic or an F test statistic has 2 degrees of freedom, unlike the chi-square and the t values, which just have a single. The degrees of freedom for an F test statistic, there needs to be 2. For between the groups, it's k minus 1. That's the numerator, and the denominator is within group, and that's n minus k, whereas big N is the total sample size, k is the number of groups. Okay, so here it would be the number of groups minus 1 in the numerator, and the sample size minus the number of groups in the denominator. This is an ANOVA table. Again, we will see the output in RStudio, but each of these has a degree of freedom. So the between group variation is k minus 1, the within n minus k, right? And then the total degrees of freedom is n minus 1. Right? This is sum of squares, this is mean square, and we use this progression. So we find the sum of squares, we find the mean square, and then we take the ratio. So often the F statistic is known as an F ratio because it's mean squared model, or mean squared between divided by mean squared error. Okay, that gives us our F ratio with these degrees of freedom, again, numerator and denominator, and we can find a p-value associated with our F statistic. Okay, so we find the F ratio, or the F value, dividing the mean square between group variance by the mean square within group variance, or mean square error variance, right? Then we use the 2 degrees of freedom. Okay? The decision will be to reject the null hypothesis if the F ratio from the table is greater than the F critical value, right? So we set the alpha, again, normally it's 0.05. So if our p-value is less than 0.005, we can reject the null hypothesis, right? And say that at least one mean is significantly different than the others. If we cannot reject the null hypothesis, then we say that all the groups or populations or treatments do not significantly differ from each other. If we reject the null hypothesis and we accept the alternative hypothesis, we need to figure out which group or groups are different from which other group or groups, right? And we do pairwise comparisons using t-tests to do that. Multiple comparisons. So we'll compare group A to B, A to C, A to D, then B to C, B to D, C to D, right? All the potential pairwise combinations. We do this using typically Tukey's, our students' standardized test multiple comparisons, and we make an adjustment to our p-value. We'll get into that in a second. Okay. So let's look at some example data here. Here's 3 groups, small, medium, and large individuals, and the values for each one. So we've got 1, 2, 3, 4, 5, 6 individuals in each group. We can find a group mean, which is in red here, and an overall mean. So if we took the mean of all of these values, all 18 versus just 6, we find a grand mean versus a group or treatment mean. Then we can calculate the standard deviation and the variance. Okay? Again, descriptive statistics is important. Now what we do is calculate the sum of squares total, SST, right? And this is basically the total amount of variation in the data. We subtract the grand mean, so in this case 6.78, from each observation and then square it and then sum those together. So we would be 6.78, so it'd be 4.5 minus 6.78, 3.2 minus 6.78, 5.5 minus 6.78. We do that, and these are the 18 values that we get. We square those, and now all of our negatives turn to positives, and all our positives stay positive, and we sum those together for a total of 61.07. That's our sum of squares total, right? That's basically an estimate of all the variance in our data. Now we calculate the sum of squares treatment. This is between treatments, okay? In this case, we take the group means and we subtract the grand mean from the group mean. So in this case, 5.27 minus 6.78 squared plus 6.52 minus 6.78 squared plus, right? So the sum of squares for each group, right? So we want to look at, this is between group differences, right? And in that case, we get 32.88. Now what's left is the sum of squares error, or the amount of variance within each individual group, right? So we've calculated the total variance, the variance between groups. Now all that's left over is the variance within groups. And this is easy because we've got 2 of the 3 components, so we can take the total minus the between, and that gives us the error, right? And that's 28.19. Okay, so again, if we go back to the ANOVA table, here's total, here's within, here's between. We calculated total, we calculated between, we subtracted those 2 to find within, or error, right? Giving our sample size and our group size. So here's the table we would get for those 18 data points, right? So there was 3 groups, k minus 1 is 2. There was 18 samples and 3 groups, n minus k is 15. And then 18 samples minus 1 is 17. The F ratio, again, we've determined the sum of squares, right? Then we divide by the degrees of freedom, and that gives us our mean square, right? So here, if our sum of squares is between groups is 3.28, we've got 2 degrees of freedom there. That gives us 16.44. That's our mean square between. Here's our mean square within, 28.19 divided by 15. Take that ratio, 16.44 divided by 1.88. That gives us an F ratio of 8.74. That would be associated in an F table with a p-value or a critical F value given an alpha level. Okay? And we would make a decision on as to whether we accept or reject the null hypothesis there. The data in the RStudio example that we're going to go through, this is another example of an ANOVA that we could do in RStudio. In this case, we've got 4 different scents, and we looked at the number of tongue flicks a snake gave in to a Q-tip coated in one of these scents over 60 seconds, right? So we had a Q-tip that was rubbed on a toad, one that was rubbed on cod, one that was rubbed on mouse, and one that was just dipped in distilled water as our control. Okay? This is a number of tongue flicks by each snake over the course of a minute for each of the 4 scents. We throw that into RStudio. We can create a nice visualization of that data. This is a box plot. So we can see that the mean here is shown in the black line and some measure of variance with the whiskers or the bars, right? So notice that a box plot is much more appropriate than a bar graph because we get a sense of the upper and lower sort of bounds of the variation rather than every bar starting at 0 and going up to its maximum, right, or up to its mean. Okay. RStudio is going to put out this ANOVA table. We can see scent here is our grouping, our treatment. Residual is the error. We got degrees of freedom. We got mean squared error here, and our F value is 1.08, associated with a p-value of 0.154. So if we've got an F value of 1.801 and with degrees of freedom 3 and 80 and a p-value of 0.154, what is our interpretation of this data? So again, assuming the standard alpha cutoff of 0.05, which again is totally arbitrary, but one that we give you, we actually would fail to reject the null hypothesis here, and we would say that the mean number of tongue flicks in 60 seconds does not differ between control, fish, mouse, and toad scents, right? If we did reject the null, then we would need to go on to do multiple comparisons, right? We would do a series of t-tests looking at just 2 groups at a time. So here we would do control to fish, control to mouse, control to toad, fish to mouse, fish to toad, and then mouse to toad. We would do every possible pairwise comparison, and we would do that looking at a series of t-tests. Now when you do that, we inflate the chance of making a type 1 error because we're using the same data to do multiple tests or inferences from, right? So we have to correct our alpha level, and what we have you do is what's called a Bonferroni correction, right? And that's simply your given alpha, which in our case is 0.05, divided by the number of pairwise comparisons you're going to make. So if you're going to make 3 pairwise comparisons, it'd be 0.05 divided by 3. In this case, 1, 2, 3, 4, 5, and 6. In the case of this data, we would take 0.05 and divide it by 6. That gives us 0.0083. That's our new cutoff to say that there's a difference between the groups. So in every t-test we do of those pairwise comparisons, we would look at the p-value associated with that test. And if it wasn't below or less than 0.0083, we would say that group isn't different. And again, we do this so that we don't conflate or inflate our chance of making a type 1 error. So we adjust our alpha level to the fact that we're making multiple comparisons. Again, like every statistical analysis, there's assumptions that underlie it, and we have to meet these assumptions in order to be confident in our interpretation of those results. So the ANOVA assumes that samples are independent and identically distributed. This is a basic assumption of any statistical model. The data are from a random sample of a population that are independent of each other. Variances are homogeneous between groups or among groups. We assume that the variance in one group is the same as the variance in another group. This one is tricky, right? The residuals are normally distributed, meaning that we're assuming the raw data is from a normal distribution. Samples are classified correctly, so the grouping variables are correct, and that the main effects are additive, right? There's no interactions between different factors. Some of those ANOVA is robust to, some of it is not. Again, depending on sample size and the variance, you may or may not have to try a different analysis because ANOVA is not appropriate. Okay, let's take a look at this in RStudio. I'm going to use a data set that has 3 species of roach and looking at their mass-specific metabolic rate. Again, don't get me started on whether mass-specific metabolic rate is appropriate or not. Okay, so I'm going to assume that you've downloaded the file as a CSV file and you've put that in the folder that you want to work in the entire semester. Again, that's the first thing we do. We download the data and we put the data from where it's downloaded into the folder we want to work in. Please, please, please create a folder on your device for RStudio. If you're using the cloud version, again, you're going to have to download that file and then upload it to the cloud so that you can use it. Once that's done and we open RStudio, again, the first thing we want to do is set the working directory. We can do that by typing set wd and then the folder path description. Again, changing backslash to / because RStudio does not like backslash. Or we can do session, set working directory, choose directory, and navigate it in the windows and click open. Okay, notice how now in my console I have it in purple that I have up here, right? It's the same command, I can run it up here. Now I'm telling R to look in the folder that I want it to look in and to save it to the same folder. Okay. Now I need to bring my data in so that R can work on it, right? R can't work on data that it doesn't know exists. So I'm going to call this ANOVA.data. So ANOVA.data assign to less than dash, right? And then read.csv, oops, I don't want that. Read.csv is a command, right? So we're just going to tell RStudio to create a data frame called ANOVA.data, and we're going to assign to that data frame the data in this file. So we're reading from a CSV, and in this case, the CSV is named roach ANOVA.data.csv. We want the file name in quotations exactly as it's saved in your computer. Okay. Remember, I use these underscores quite a bit because RStudio doesn't like spaces. Okay. If I run that, now we can see that up in my environment panel, I have ANOVA.data, 156 observations of 2 variables. If I want to view that data, I can type view and then ANOVA.data, because that's what I've named it. And now you can see I've got species here. So this is dubia roaches and hissing roaches and red runners. So I've got 3 species of roaches in the species column, and then mass-specific VCO2 or mass-specific CO2 production. Okay. I can view the structure if I want, str lowercase, and then in parentheses ANOVA.data. Okay, that's a data frame. It's got 156 observations of 2 variables. Species is the first variable. It's a character, and this is either going to be DB, HS, or RR. Mass-specific VCO2, again, notice that how it's spelled. When we type it in, we have to match it. This is numerical, right? So everything checks out. Now what I want to do is plot my data. I'm going to use the function box plot. Okay, so notice how RStudio wants to help me out here. There are 2 ways to start this out. So notice now when RStudio brings it up, it has the parentheses, it's got the X. So I can list the X variable and then the comma the Y variable, right? So if I did this, I would do, and then say ANOVA.data $, X here, right? X is my independent variable, in this case the categorical variable, species, and comma ANOVA, oops, gotta spell ANOVA right, otherwise it's not gonna work, data, $, now my Y variable, mass specific VCO2, okay? And then I could go on and finish this. If I use this comma here to separate my variables, I have to list X first and then Y. Okay? Again, visualizing your data, you have to do it appropriately. So if you use the comma form, it's the X variable or the independent, then the dependent. I like to use the formula here. So here it's mass specific VCO2 and then this tilde, okay? This is y basically equals x. This is a formula. So this is saying y variable tilde x variable. Notice that the orientation is different. If I mix this up, RStudio is not going to know that I don't want you to have the categorical variable on the y-axis. I want you to have it on the x-axis, right? And so it's going to give you a plot, but not a plot that's appropriate for the class that we're going through. Okay, so you have to make sure you have your variables in order. The independent variable in this case is the categorical variable. That should be on the x-axis. The continuous variable, the dependent, should be on the y-axis. That's why when I list it this way, it's y and then x. But if I did the formula with the, if I didn't do the formula with the tilde and I just did a comma that separated them, it would be x and then y. Okay. In this case, I'm giving it the data file right away by using data frame $ variable. Here I'm using the variables and then telling it what data I'm looking at. But the rest of the formula would be the same. Here's the y label, mass y lab equals, and then in quotations what you want your y-axis to say, comma x lab, x label. What do you want your x-axis labeled as? Again, in quotations, it's going to put exactly what you spell. If you misspell it here, it'll misspell it on your plot. And then main equals, and then in quotations, whatever I want there. For many of the assignments, we're going to ask you to put your name here, right? And so you're going to need to demonstrate that you can alter the code by knowing where to put your name. And so here I can put my name in the main graph title. Okay, it's in quotations, comma. Now, if I want my boxes to be different colors, which is always visually pleasing, right? I can say COL, which is colors, equals C, which is concatenate. So we're going to assign these colors. And then again, if we, let me go back here. If I just want to see what colors I have available, I can type COL and then open and close parentheses. Oops, apparently I can't. Never mind. I'm going to sidetrack myself there. You can tell R to give you all of the colors that are there, right? One of the ways we know that the colors labels work is that it turns the color, the text is turned that color in RStudio before you execute the code, right? So if I spelled green wrong, you notice that the color of that text didn't change, but now if I type green correctly, oh, the text is now colored green. So here I've got three treatments, DB, HS, RR, right? So dubia, hissing, and red runners. RStudio is going to put those in alphabetical order. So whatever I want DB to be should be the first color I list, then HS should be the second color, and then RR should be the third color. Since RR is red runners, I called that one red. The others, it doesn't really matter, right? I could change this to, oops, gotta spell purple right though, right? See, and now it turned purple, right? Then I close that parentheses and close the final parentheses. And boom, now I've got my name and this long title. My Y and X axis are labeled, and I've created a box plot, right? That is a much better visualization of the means and variances within each group as compared to a bar graph. Okay. Again, if I wanted to change this back and I said, it turns out I don't like purple, I just change that one, rerun it, now I've got it in blue, right? And now I can export, I can save it as an image, I can save it as a PDF, I can copy that to the clipboard and paste it into another file. Now I've visualized my data. Now I need to run the actual ANOVA. So I'm going to create a new item or object, excuse me, called roach.anova. Again, less than dash assign to. And then AOV, that is the command or the function that is going to run an ANOVA. Okay? And I use the same formula I used in my box plot, the dependent mass specific VCO2 tilde and then independent species, comma, and then what data frame? Data equals ANOVA.data. Okay? Then I close that parentheses. This is going to, now we can see up here, it's roach.ANOVA. This is a list of 13 items. Notice it doesn't output it down in my console, but I'm going to want to see what those results were, right? So I can type summary and then in parentheses roach.ANOVA. And now look at my console. I've spit out my ANOVA table. Okay? Species is my among, residual is my error. Here's my degrees of freedom, 2 and 153. Sum of squares, mean squares, my F value or my F ratio, 21.66. And now my P value, F or 5.21 times 10 to the negative ninth. I've got 3 asterisks next to it, basically saying that it codes as 0, right? So 5.21 times 10 to the negative ninth is much smaller than 0.05, right? So I should be able to reject my null and say there's evidence to support the alternative hypothesis that at least one of these species is different than the others. Okay. Well, since I've got 3 groups, excuse me, but I only know that at least one of them is different, I have to figure out, excuse me again, which one or ones are different from each other. So I'm going to do my multiple comparisons, my pairwise t-tests. I'm going to do that using the Tukey t-test. And so I'm going to create a new object that's roach.ANOVA.Tukey. I can name this whatever I want. That's simply the name of the object. Assign to, again, less than dash. Now the function is Tukey with a capital T, everything else is lowercase, and then capital HSD. Okay? And then I'm going to tell it what object to do that on, and that's my roach.ANOVA. Okay? So now I'm telling it to create a new object called roach.ANOVA.Tukey, and in that it's going to be all the pairwise comparisons of my groups. So I run that. All right, now it's a list of 1. It comes out in my environment window, and now I need to see that, so I'm just going to type roach.ANOVA.Tukey, and here comes my list. Okay, so here's my comparison. In this case, it's hissing versus dubia, or HS to dB, RR to dB, RR to HS. Here's the difference, the lower and upper confidence interval. This is what I'm interested in, my adjusted p-value. 0.1329, 0.00003, 0.00000, right? Remember, we're going to do a Bonferroni correction. We have 3 groups. We made 3 comparisons. 0.05 divided by 3 is 0.017, essentially. Any p-value less than 0.017 would be a significant comparison. Okay? This is telling me that HS and DB are not different from each other. That p-value is 0.1. But red runner, or RR, is different from the other 2. So if we look at this, this is telling us that these 2 groups are basically the same, but this group is not and tends to have a higher mean than the other 2. And so in this case, one group is different from the other 2, but those other 2 are not different from each other. Right? So again, the overall interpretation would be that I reject the null hypothesis, and there's evidence to support the alternative. More specifically, RR, or red runner cockroaches, have a higher mass-specific metabolic rate than dubia and hissing cockroaches. Right? A significantly higher mass-specific metabolic rate. Okay? So I collected my data, I visualized it, I ran the ANOVA. Given that I rejected the null hypothesis, I ran my multiple comparisons, my Tukey t-tests, and now I can make inferences based off of those results. I would need the visualization, I would need the output of the ANOVA table, and I would need the output of the multiple comparisons in my interpretation.